Okay. So our next speaker in the morning is Gou Nakamura from Aichi Institute of Technology, and that's the title of his talk. So go ahead. Thank you, Gou.
Thank you. First, I'd like to express the organizer and know and any other organizers.
Yep.
For giving me an opportunity to have a talk in this workshop. So, let's start. So, this is the table of contents, and keywords are extremal surfaces, compressed doubles, and model of Teichm space of genus 2. And the last section, the coordinates of some kinds of two marked closed Riemann surfaces in the Teichm space. So, so far I have studied extremal surfaces. I use the term extremal in the sense that the surface contains the largest radius. The radius is determined only by the Euler characteristic. And here, my target is genus 2 surfaces. So, an extremal Riemann surface of genus 2 has a hyperbolic regular Teichm as its fundamental region. And the next target is extremal Klein surfaces of genus 3. This has a fundamental region and the regular parallelogram as its fundamental region. Next, if we take a complex double of the extremal, I mean, Klein, I use the term Klein in the sense that the surface is non-orientable, right?
Mm-hmm.
So, if we take the complex double of extremal Klein surface of genus 3, we can get symmetric Riemann surface of genus 2. We denote it S sub 3. And it has hyperbolic Teichm as its fundamental region. So, we consider the difference between the two surfaces. One is X and one is the symmetric surface C. Both have the same number of sides. So we are interested in the difference between two surfaces with similar side time patterns. So to investigate the difference as an attempt, I give a marking of these two surfaces. So to investigate two surfaces in the Teichm space. So to give a marking, I use the information about wire reference points. So finally, I calculated the difference distance of these two marked surfaces. First, I explain extremal surface. Let S be a compact, orientable. Let S be a compact, orientable, or non-orientable hyperbolic surface of genus Z. So, and let D denotes the unit disk. And so, as you know, the surface hyperbolic surface S is equipped with a hyperbolic metric induced by the metric of unit disk. So, the radius R of a metric disk embedded in S verifies the following inequality, which was shown by Babar in 1996. So the inequality is like this. The hyperbolic sign of R is less than or equal to just a number. Here, chi sum Z denotes the Euler characteristic. ordinary characteristic. So we call S an extremal surface if it contains disk of which radius satisfies in equality in 1. And we call the disk extremal disk. Okay. So the next is important. If S is extremal, then its fundamental polygon is, we can take its fundamental polygon a regular 6 minus 6 Klein polygon. Oh, so that is a regular 12G minus 6 ohm or 6G minus 6 ohm according to the orientability. So this slide shows extremal Riemann surface of genus 2. So Girondo and Andreas Diaz in 2002, it was 20 years ago, they showed that 20 years ago, there exists exactly 9 extremal Riemann surfaces of genus 2. And all the centers of extremal disks are obtained. And they also obtain the worst points and group of automorphisms for these surfaces. So this picture shows side parent patterns of extremal surfaces. So in the states, there are 9 extremal surfaces, but this picture shows 8 side parent patterns. Because the 9th one is obtained from and it's export. So the mirror image of export, mirror image or export determines another Riemann surface. So, but essentially there are 8 side parent patterns. And the two sides connected by orange curves are paired, identified on the surface. And the red point indicates the centers of extremal disks. Okay. So how about extremal plane surfaces? So in 2007, so it was also more than 15 years ago, there exists exactly 11 extremal surfaces, extremal plane surfaces of genus 3, and all centers of extremal disks are obtained. We also determine the group of automorphisms of these surfaces. So this figure shows the side parent patterns and the centers of extremal disks. So it is difficult to see, but there are dotted orange curves. So, so two pairs connected by dotted orange curves are paired by non-orientation reversing Lewis transformations. So the dotted curves characterize the non-orientability of the surface. So this table shows the group of automorphisms of the 11th plane surfaces. They are very simple group. The reason why this is simple is that the automorphism is restricted to preserve the to fix the center of extremal disks or interchange the center of extremal disk. So such a restriction makes the group simple one. These are all the results of our old results. So, next term is complex double. So let me remind you about this term. First, take a non-orientable surface S, the left side. So in general, the surface may have a boundary. So this picture shows one. The genus of Klein surface means the genus means the number of crosscuts. Okay. So this is the genus 1 boundary 2 Klein surfaces. So there's a 1 crosscut, 2 boundaries. So to make a complex double, we have a copy of the surface S and open the crosscut and paste 2 surfaces properly. Then we got the compact orientable surface S of C. S of C is the complex double of the surface. So from here, we will try to create the complex double of the first Klein surface S1. This one is, of course, the first Klein surface. So I label the side of the polygon from 1 to 6, and 2 sides connected by dotted curves is labeled, for example, 1 and 1 star, and 2 sides identified by connected by orange line, orange curve is 2 and 2 prime, and so on. And next, this slide shows the left one is the first picture, and the right side is the mirror image of the left side of polygon. Right is a mirror image. Then I connect 2 polygons like this. So the difference is left side one is connected, pasted to the right side 1 star. And for example, one star, four star is connected to right side 4. And the original orange curve is preserved. Keep the original orange. So in this station, this polygon has 22 sides. So to make the polygon convex, we added 2 red curves, red sides. So this convex part is removed to this concave part, and this convex part into concave part. So we get suitable fundamental region of the complex double. This has a size, and this is 18 bond. This is 18 bond. So try to such a procedure for all 11 subsets, we get 11 fundamental regions of the convex double. Of course, these are symmetric Riemann subsets. So next, I want to find wireless points of these symmetric Riemann subsets. In 2003, Gou and Martin determined the 6 wireless points of genus 2 surface with a regular fundamental region by finding the intersection points of non-dividing simple parts, simple closed geodesics. So following their idea, we obtain the wireless points of these surfaces. So this figure shows the wireless points for 11 symmetric Riemann surfaces. So, for example, the first figure shows that this is blue. The blue points are the wireless points, and these geodesics are the axis of cycling maps of Teichm group. So fortunately, I can get 6 points for all of them. Next, I want to show a model of Teichm space or genus 2. Shara defined Teichm space T sub z of genus Z by using so-called canonical polygon in 1999. Following the idea, we give a model of the Teichm space of genus 2 and consider a global coordinate system of Teichm. So canonical polygon is like this. This is a canonical polygon. So the important point is the opposite sides have the same length. So the length of A1 is equal to the length of A5. A2 is equal to A6, and so on. So, and in genus 2 case, each opposite boxes have the same angle. So rotate this polygon around the center. Half turn makes half turn indicates the hyperelliptic involution. So various points appear in the center, and each midpoint of sides, and every vertices is 1 point on the surface, on the closed surface. And we introduce 7 lengths from x1 to xn like this. So x1 is hyperbolic sine of a1, and x2 is hyperbolic sine of a2, and x3 is a3. And next, x4 is the length of half length of b1, hyperbolic sine of half length of b1. b1 is the segment between two opposite vertices. This is B1, and next B2 and B3. So okay. So we need 7 values. So using these 7 values, we get coordinate system of the Teichm space of T2. So it's agree there exists an ending of T2 into R7, where the all entry is more than 1. So rectifier is this entity. So S is magnitude from x1 to x7, and these 7 numbers satisfy the following 3 conditions. I forget. This is 2012. So it is more than 10 years ago. So today my talk is very old one. On that. So it reveals that I haven't worked recently. Anyway, so the first one, so there are this here there are new letters A, B, C, D, and X, Y, Z. This is determined by these 7 numbers, like this. So it is very complicated. So I want so nobody wants to see this. So but anyway, the first condition. This is the so-called triangle equality. So there are 3 triangle equalities. This enables us to make 3 hyperbolic triangles. And the second one is secant inequality. Means the so-called angle condition. So this enables us to make the fourth triangle. And the third one is area condition. So four triangle at the area, the total area of 4 triangles equal to 2 pi. 2 pi is the half area of the compact Riemann surface of genus 2. So this is the characterization of T2. So microphone. 5 minutes. So in the Teichm space, in our Teichm space model, I calculate the coordinates of 2 Riemann surfaces. I didn't say anything. This is the compact Riemann surface, and it has a marking from the size of this polygon. So the size of polygon is the curve on the surface. So that's a marking. So the right side is hyperbolic polygon of S1, S1C that appeared before. And X2 is also appeared. This is the extremal Riemann surface in genus 2. And the X sub 2 means the second one. So the important thing is that these two polygons have a similar cycling pattern. Okay, similar cycling pattern. So I want to know the difference of these two surfaces. So to calculate the coordinate of these two surfaces, I cut the polygon suitably. So the blue points at various points, and divide the polygon via geodesics to these various points. So, and cut and paste, after cut and paste process, we get these two canonical polygons. So, to emphasize this is canonical, I will do these polygons slightly up around the center of the piece. So, it is easy to see that the opposite sides are the same length. These are canonical polygons. And calculate the surfaces coordinate. It is, of course, approximation value. The left side have this coordinate, and right side inner surface have a coordinate like this. The red number is the length of the red number is the length of the left side, and so on. So to define the difference, we introduce a distance in vector space like this. So I think it is a natural one. This is this is a kind of distortion of these two surfaces. So by using this distance, I can calculate these two marked Riemann surfaces. So it is approximately 2.347. So I'm really happy to calculate this number, but most of people think that I'm then. So I agree with you, but today my talk is I already calculated this number, this distance, and I hope this will contribute to the analysis of pattern space. So, gracias.
Questions?
Is it obvious that definition 5.1 is a distance? I mean, it's a
Yes.
triangle inequality.
Yes. It is easy calculation. Yes, no problem at all. Yes, of course, it is distance. Yes.
So your coordinates depended on a choice of the ordering of your Weierstrass points.
Yes, that's right.
So is there a different ordering when you get a different number?
This is different ordering means a different marking.
Yes.
So this coordinate is determined from this marking. So if we change another pattern space process, we have of course the same Riemann surface, but another mapped Riemann surface. So this is another point in pattern space.
So perhaps it would be good to have a distance that did not depend on this choice of a like an invariant, some sort of invariant distance.
It has to depend on the mark. It's a marked. You're looking at marked metrics. It has to depend on the marking somehow. Right?
You're in Teichm space.
You're not a modulus space.
I don't see the surface on the modular space. In the marked, you must have in the tensor space.
I guess possibly what I'm asking then is, what is the closest distance in the modular group orbit between these two? Not the distance between the particular points.
Yes, actually, today I didn't show anything, but I have some mapping class group on this surface. So if I map this surface by the reducible element, so and move the point. I can separate the movement where it is the closest one is I can I'm trying to say this is not so I don't have every mapping class group, so I didn't anything about is it maximum, min number, or so. I'm under construction.
Questions? Okay. So you can go again.